Good afternoon again. This is the second video in the series of videos of me explaining chapter 13 as part of my assignment. And in the previous part, we ended at modeling combustion air. So in this part, we will be going over the air-fuel ratio. Wait, let me just get rid of this. Okay. So in this next part, we're looking at the air-fuel ratio. Now this well, it is what it says on the box. It is the ratio of air to the ratio of fuel that's being used. Now, why would this value even matter? Why is this a useful value to think about? Because when you're pulling in air, right, and you're pulling in fuel into your engine, okay? Let's say the relative amounts of these two, you need to determine in order to be able to get the ratio just right, where you're not getting an incomplete combustion. So what does that mean? If you have a case where the air-fuel ratio is very low, so if AF is very low, there's a chance that there's not enough oxygen for a complete combustion. So then you're getting an incomplete combustion. And as we've stated before, an incomplete combustion means less energy, so a smaller enthalpy change overall. And it's going to mean you're getting less workout. And so the efficiency decreases. So this is an important value to think about because it tells you, okay, this is the amount of oxygen that I'm pulling in relative to the amount of fuel that's in that reacting mixture. And another reason why you should care about this air-fuel ratio is due to the fact that sometimes if the air-fuel ratio is too high, okay, if it's too high, sometimes it can mess with the reaction because now remember that air is mostly nitrogen, okay? If you have too much nitrogen, yes, you're getting the complete combustion because there's a lot of oxygen, okay? But since there's a lot of nitrogen as well, and nitrogen really does not do anything, it can drop the temperature, okay? Because you're getting the same amount of heat from the complete combustion at a certain threshold. But now you've got more air in that reaction mixture. So the temperature might drop. And we know that the heat transfer at a lower temperature decreases the overall efficiency of a thermodynamic process. So this air-fuel ratio is an important value because it needs to be just right for your engine to be very efficient. Now, it can be calculated on a molar basis, where you have moles of air over moles of fuel, or it can be calculated on a mass basis. And note that these two values will be slightly different. And actually, it will be different by a factor that is determined by the molar mass ratios of air and fuel. So you can get the molar mass of air, molar mass of fuel, you can get this ratio, and you can have the molar basis ratio, and you can just get the mass basis ratio as well. Now, under the next part, we have what's called the theoretical amount of air. This is just the minimum amount of air that you need for a complete combustion. So the thing is, usually in practice, you're not getting exactly the theoretical amount of air. Ideally, you would get you would get the theoretical amount of air, but it might not be always possible in practice. So you might be getting less than this, or you might be getting way more than this. And the excess or the deficiency, we usually write as a percentage, as you can see here. Okay. Now, also, by the end of the reaction, there shouldn't be any free oxygen, which just means that the reaction is just complete. Okay, so on to the next part is exploring combustion concepts. Now, after we write down the balanced equation, as we've mentioned before, we usually include nitrogen in our chemical reaction, even though it's not reacting. On both sides, it should be the same amount, right? And you can see that the nitrogen has been left unreacted. It's N2 and N2 here. However, we still include it because it is important for us to calculate the air-fuel ratio, because the total number of moles of molecules within the air, you can only determine by first determining the amount of oxygen that you have to pull in, and then because we know that for every 1 mole of oxygen, there's going to be 3.76 moles of nitrogen. You can do a simple calculation like this, get the amount of moles, okay? And then you can just plug it into this formula. And since there was only 1 mole of methane, the ratio happens to be 9.52 over 1. Now, in the same manner, you can include or you can factor in the theoretical, the excess of air compared to the theoretical air. And as you can see, since it's 150%, they've scaled it by 1.5. And this has resulted in the air fuel mixture being scaled up by 1.5 as well. Now, the next part is what we call a dry product analysis. Now, we know that in practice, most of the combustion reactions that we get are going to be incomplete, right? And it's not always possible to do calculations to know exactly the amounts of carbon dioxide that you're getting or the amount of water that you're getting. Okay, so you can't know the exact amount without measuring it, without some sort of measurement. Okay, and the devices that we use to measure the amounts of products usually leaves out water. So in such a scenario, we call this analysis a dry product analysis because we're excluding the water from our measurement and we're just measuring the dry products. And after measuring the dry product, well, here as an example, you can see that it says ethanol is burned with air to give products with dry molar analysis. So you get 3.16% CO2, 16.6% carbon monoxide, and 80.24% nitrogen. And based off of this, you can write the chemical reaction. Well, you can just write these percentage values as moles values, and it will give you the ratio of the moles of for this particular reaction. So you set up this equation, you use the mass balance on both sides because on both sides the amount of elements should be the same. And then you can find the values of A, you can find the value of B, you can find the value of C. And here they've done this exact same thing. They first balanced it, and then they found each value, essentially. Now, for the next part is the energy and entropy balances. So I will be leaving this video at this part. I will be ending it here. In the next video, we will be looking at this part, hopefully. And so this is the end, and goodbye.